Cool. All right. Welcome everyone to the last session for the deep learning bootcamp. Hope it's been fun. I've seen the numbers have gone down, but you guys are the strong. So good job. So we have one last session, which is on fine tuning, which I maybe probably came up during the past days. And also with fine tuning, we'll show a lot of Hugging Face tools and functionality that can really help when you go about fine tuning or different techniques. I think Hugging Face was also mentioned a bit during the days. Did you use it during the week? Tiny bit? Okay. So here we'll see some quite useful packages that they provide, which are quite a lot. When I was preparing this yesterday, I found out they had so much stuff. So it's a lot of gold to dig into. So I guess most of you know me. So I'm Eric, doing a PhD here at EPFL. So I previously worked in SNP Sonos where I had to do some machine learning, but never using really the tools that I had to use here because usually a lot of things are custom within a company. But a lot of this stuff that you'll see with Hugging Face are quite useful in your course projects or if you want to quickly see if you can make a model perform well on your data or for your task. So hope it's useful. So the outline for today, we'll introduce fine tuning, what it is, why you do it, how you do it. We'll look at a few examples, or I mean, most of the examples you'll see it in. So vision, language, audio, image generation. We'll only really look at code for the first two, because I think that'll give you kind of the general idea of how you go about this. And then the last two, I just provided some links so that then if in your time or if we have time later today, maybe you can try out some of the examples that I've linked to. And then we'll talk briefly about zero shot, which may have been mentioned, I think, in Federico's talk with Clip. So I'll just give some more links to that. So just another way that you can avoid training, essentially, which could be useful. So what is fine tuning? So essentially, we take something general purpose and make it specialized. So in the case of in machine learning, deep learning, for example, you could take GPT-3, and what they did is they fine-tuned it for chat, which is what made ChatGPT. So if you see these ChatGPT or instruct, when you see those labels, essentially they fine-tuned it either for chatting interaction or instruct, where you want to give commands to the GPT. If you've used Copilot, it's the same thing. They've taken something like ChatGPT, they fine-tuned it for the use case of coding. And more generally, you can think, okay, if you have like a doctor, they had their general training, probably in their early years of their medicine studies, and then they can be specialized into, cardiology or dermatologist. So that's the general idea. We're going to take something that has seen a lot of general information and hopefully exploit that to then go deeper into a specific application. So why would you want to do fine tuning? So in this paper, it was shown, for example, if you compare GPT-3, which had 175 billion parameters, it actually performed worse than a GPT model, which was smaller, but which was fine-tuned specifically for this instruct use case. So if you were looking at this instruct use case, what this paper was showing essentially is that this smaller model was able to perform better than this large general purpose model. So already we can see some advantage. You can have a lot less memory consumption and maybe be able to fit smaller models into your use case or your device that you're working with. So some other benefits. So you can customize to a specific use case for improved performance or have a smaller model for similar performance. And this can help for reducing hallucination because maybe your model hasn't seen specific examples. Like if we take the medical example, maybe it wasn't trained at all to deal with medical queries. So then it's going to just make up stuff if you just use a general purpose model. You can steer the model for more consistent outputs. So for example, maybe if you worked if you tried ChatGPT, you can see sometimes it gives really long responses, and maybe you want to have a more consistent, snappy output. You can have, instead of having to train a model from scratch, this can use up less time and cost to actually train this model, given you have a proper data sets. And as we saw before, you can get to a smaller model, which could work better for on-device or on-premise, or they call on-prem usage, which could be better for privacy, so that maybe you don't need to always make API calls to a large model like on OpenAI or Mistral's interface. You can really run it on maybe your laptop if you're doing like a prototype or demo, or on your company's servers. You can have lower latency since you have less of this back and forth. You can work offline as well too. And you could have a lower cost because then you don't need to depend on an external service to get queries. I mean, it could also depend what are your own electricity costs, but then probably in most cases, if you have a smaller model and running it locally, it'll be cheaper than always having to query an API, especially at scale. You can have better control, which is kind of linked to the first parts. All right, so I found this video, which I thought was useful. So it gives some nice visualizations. So I didn't have to just create new slides for you. So I think we can watch this, which takes about 5 minutes, and it'll give some nice context and visualizations of what fine tuning involves. So let's hope the audio works.
Transfer learning occurs when we use knowledge that was gained from solving one problem and then apply it to a new but related problem. For example, knowledge gained from learning to recognize cars could potentially be applied in a problem of recognizing trucks. Fine-tuning is a way of applying or utilizing transfer learning. Specifically, fine-tuning is a process that takes a model that's already been trained for a given task and then tuning or tweaking that model to make it perform a second similar task. Assuming the original task is similar to the new task, using an artificial neural network that's already been designed and trained allows us to take advantage of what the model has already learned without having to develop it from scratch. When building a model from scratch, we have to try many approaches in a type of trial and error sense. We have to choose how many layers we're using, what types of layers we're using, what order to put the layers in, how many nodes to include in each layer. We have to decide how much regularization to use, what learning rate to use, etc. So with this, it's easy to see that building and validating our own model can be a huge task in its own right, depending on what data we're training it on. That's what makes the fine-tuning approach so attractive. If we can find a trained model that's already done one task well, and that task is similar to ours in at least some remote way, then we can take advantage of everything that model has already learned and apply it to our specific task. Now, of course, if the two tasks are different, then there will be some information that the model has learned that may not apply to our new task, or there may be new information that the model needs to learn from the data regarding the new task that wasn't learned from the previous task. For example, a model trained on cars is not going to have ever seen a truck bed. So this feature is something new the model would have to learn about if we're going to be training it to recognize trucks. But think about everything else that our new model for recognizing trucks could use from the original model that was trained only on cars. This already trained model has learned to understand edges and shapes and textures, and more objectively, headlights, door handles, windshields, tires, etc. All of these learned features are definitely things we could benefit from in our new model for classifying trucks. So this sounds fantastic, right? But how do we actually technically implement this? So going back to the example we just mentioned, if we have a model that's already been trained to recognize cars and we want to fine-tune this model to recognize trucks, we can first import our original model that was used on the cars problem. Then, for simplicity purposes, let's say we remove just the last layer of this model. This last layer would have been previously the layer for classifying whether an image was a car or not. After removing this, we want to add a new layer back whose purpose is to classify whether an image is a truck or not. Now, in some problems, we may want to remove more than just the last single layer, and we may want to add more than just one layer. This will depend on how similar the task is for each of the models, since layers at the end of our network may have learned features that are very specific to the original task at hand, where layers at the start of the network may have learned more general features like edges, shapes, and textures. So after we've modified the structure of the existing network, we then want to freeze the layers in our new model that came from the original model. By freezing, I mean that we don't want the weights for these layers to update whenever we train the model on our new data for our new task. We want to keep all of these weights the same as they were after being trained on the original task. We only want the weights in our new or modified layers to be updating. So after we do this, then all that's left is just to train the model on our new data. Again, during this training process, the weights from all the layers we kept from our original model are going to stay the same, and only the weights in our new layers will be updating. Now, if you want to see all of this in action, I have separate videos in my Keras playlist that will show you how to build a fine-tuned model, how to then train that model, and then use the model to predict on new data. Definitely check those out if you want to see the technical implementation of fine-tuning written in code. So hopefully now you have an idea about what fine-tuning is and why you may want to use it in your own models. And I hope you found this video helpful. If you did, please like this video, subscribe, suggest, and comment. And thanks for watching.
All right, so now I have the audio twice. So that's the basic idea of fine tuning. Is that familiar with some people? You've seen this before? Okay. So that's one way you can approach fine tuning, which is to, as she was saying, freeze those layers. But there's some other approaches too. And then just to clear up some terminology, because sometimes things will be used interchangeably, sometimes people will mean different things. So fine tuning, what some people will use it for, especially in the LLM context, is that actually they'll typically use it to mean that they're going to train the whole model parameters on a new task with like a small learning rate. There's some other tricks, which we'll see. Whereas she also used this term transfer learning, where that's often where you freeze, as she was saying, you freeze the first parts, and then you add some new parameters and you train those new parameters. But sometimes you'll hear people use them interchangeably, and depending on the field, they'll say more fine tuning, transfer learning. I don't know, Parsa, you maybe in LLMs they say fine tuning more, and for vision they say transfer learning more often.
So transfer, but using the very original literature of NLP sometimes.
Yeah.
Mostly these days when people want to fine tune an LLM, they say fine tune.
But
and they usually don't freeze.
Yeah, I don't think they. So that's why I made this distinction here. Often fine tuning doesn't freeze, while transfer learning often freezes.
But the original idea also in transformers was that you have a head and body.
Yeah.
You freeze the body and just change the head, but sometimes people don't freeze.
Yeah. So if you were to freeze, okay, when would you want to freeze? So usually that's good in a situation where you have limited data compute because you don't have as many backpropagation, or you don't have to backpropagate as deep, and you're less likely to overfit because you're only training like maybe a last layer rather than the whole neural network. So that's maybe a situation where you want to freeze. And another term which we'll hear coming up is something called pre-training. So essentially that's you have a larger model like GPT that you've trained on general data sets and to learn general features and representations, or you would use image nets, for example, and images, and then you would go to fine tuning after that. So I have some visualizations. But as I mentioned, okay, fine tuning and transfer learning can be used interchangeably, but the general flow will be okay. Okay, you see this on my side. I have this thing which I'll close. So the first pre-training will look something like this. You have some base model, which you use a very large data sets, long training time, and lots of computes to get to a pre-trained, for example, language model. And then the step of fine-tuning or transfer learning would be you take that pre-trained model, and now this doesn't need as much computes or much time, and you just tweak a few things. You'd probably keep the same type of training approach, maybe change the learning rates, and you could add some other tricks where you add a new layer or you do some other optimization, which I'll show in a bit, and some things that are more specific for LLMs. Okay, but that's the general approach. So first you'd pre-train and then you would fine-tune. And this is like the theme these days with these large foundation models where you take something off the shelf and then you're going to fine-tune it for a specific case. It's very unlikely that you'll be doing this base model unless you're maybe really doing a completely new application where you don't have, let's say, a data type which translates to another so well. So it's usually a good first step is to do the pre-training, since it requires less time to get some meaningful results. Any questions on that? Okay, so then how do we go about fine-tuning? So first step would be, okay, we first want to figure out what is our task, what we're trying to solve. The next step would be, okay, we try to identify a base model, so a large model that has already been trained for something that's similar. So that'd be the second step. Next step would be to prepare a data set for our specific task. So that means, okay, making sure we have enough, splitting between train and evaluation. And an important part is also pre-processing that data in a similar fashion that training data was prepared for this base model. Next, you would define some sort of training configuration or strategy. Maybe you would freeze parameters, add some last parameters. Maybe you would fine tune everything with a small learning rate. Next, you would then go about training, evaluating on the test that you've created, and then you would probably be iterating between these steps. Maybe you realize, okay, I need to get more data for a particular edge case that's not working so well. Maybe you figure, okay, I need to train a bit more actually, or I had too high of a learning rate. Maybe I need to add some more parameters because it's not performing as well in that use case. So practically, for example, if you want to do something like book review, sentiment classification, maybe you would take a large language model or something a bit smaller like Dilbert, and you would want to work with one of those. You would collect the data for your specific case and pre-process it like they did it for those models. And then you would, yeah, go through those later steps. Any questions? You said no, Peter? Or
I'm not sure about pre-process like training data, so it's usually the case, but not always.
Is there a case where you think that you don't need to pre-process? Because then,
yeah, like, maybe for self-supervised models.
One thing is that maybe you can also change the structure of the text and have it learn the new structure. Maybe sometimes do it on LLMs.
Okay.
We impose a certain structure that you also learn in fine-tuning. But still say, okay, there is a pre-process, right? Maybe just be different, deliberately different.
Yeah, I mean, what we'll see like in these, let's say, more supervised fine-tuning and like with a lot of Hugging Face examples, usually when they give you a model, when they open source a model, they'll also open source their tokenizer or their preprocessor, and you'll usually load the two of those together. And that's what we'll see in their code. But maybe in some other applications, you wouldn't necessarily need to preprocess, as Peter and Parsa are saying, like they did for the training data. But generally you do, because otherwise it probably hasn't, maybe there's some normalization that they did or some tokenization that they did that if you do something different, your base model just it's not gonna perform as well as you expect it to. So yeah.
Sometimes you can add tokens.
Yeah.
Fine-tuning step. So there's something sometimes I've seen people do. They add tokens and then they fine-tune technically new tokens. For example, a specific start and end token.
Yeah. But those start and end, they would have seen similar types during their normal training, right?
Yeah, but you can add new tokens to the vocabulary.
Okay.
I've done this before.
Okay.
So
Parsa probably know, but I don't do LLM so much, but yeah, I would take Swift.
But yeah, normally you should start with the same recognizer.
generally try to make the distribution of new input as close as old input.
Yeah.
But if it's a bit different.
Not necessarily, because I mean, that's what we're doing when we're fine tuning. We want to fine tune to a different use case, right? A more specialized use case. So in terms of the task, the distribution is different, right?
Yeah, but by preprocessing it in the same manner, you try to make it as close.
Yeah, as close as possible, but for your specific use case. Because probably maybe it saw data like your use case in the general corpus, but now you want to kind of like push it more into that direction. All right, so let's see an example for vision. So for example, I guess you saw CNN architectures, which can work really well and don't need as many parameters as transformers, for example, because they use these kernels which kind of shift in space. And a recent trend, I guess, in a lot of applications is to switch to transformers because it kind of removes this inductive bias that CNNs have. Have you seen this term inductive bias in the course? So inductive bias is essentially you can construct your neural network so that you force it to learn in a certain way. And the inductive bias in CNNs is that we want it to be able to detect things in a shift invariant sort of way. And then people will do augmentations so that, okay, depending if it's rotating or not, it'll perform robustly, essentially. So I put some links later on. So essentially the inductive bias, that because of this bias, you can have a smaller model because you only have to learn these kernels rather than having a fully connected thing like you would have in these vision transformers. But then because of that, it's not going to pick up on global features as well in the CNN because it's going to look in really small patches. And then later on when it aggregates things, because now you pool and you bring things closer together, at the later stage, there it tries to get for more global features. But a vision transformer, it's going to look for global stuff from the very beginning because of this attention mechanism. It's going to try to look at the relationship. So for example, here's like a visualization from the original Attention is All You Need paper, where they essentially use a transformer that you would in an LLM context and break it up into patches like this, and they tokenize those patches, but you guys can correct me if I'm wrong. And then essentially it's going to be looking at relationships between all of these patches at once.
Yes, it's not attention is all you need, it's another way.
Yeah, I think this is the.
Oh, yeah.
Something works.
Yeah, exactly. Sorry. Yeah. An image is, I put it here, the link. An image is worth 16 by 16 exports. But so because of this, they can find better global relationships from the very beginning. So they're removing essentially this inductive bias, spatial bias that was in CNNs, and that allowed it to get better performance. But since you're removing this, let's say, bias that you put into the model by having kernels and having something more fully connected, you actually need a lot more data for transformers, which is why they only came later on as, okay, a new state of the art, because people needed the data to really train and beat the performance of ResNet or other CNN type of architectures. But yeah, this term inductive bias is useful because I guess it's just giving a terminology to help you think about how can I frame my architecture in such a way that it works best for my problem. So I don't have a slide for this, but in my problem, like that I do in my research, I combine neural networks with some more physics-inspired components. And there I'm putting some bias where I say, okay, I know my physical system has this type of structure. So I exploit that. So I don't need as much data as in a more general case model. But that's just like a side note on how you would pick your architecture.
When you are connecting to this physical
Yeah, I can do it on the boards instead of the slide. So this might get a bit technical, but how many of you have seen like I've done image processing courses, and do you know this concept of deconvolution? Yeah. Okay. So, can you see on the screen?
Only the right part.
Only this part?
Yeah.
Until where? Here? Here?
Here.
Okay, so I'll draw on the space then. So imagine like you have some image of a smiley guy, and then essentially it's getting blurred by some kernel. So you get like a blurry smiley guy, right? And one thing that we know is that, okay, the relationship between these two things is some sort of convolution, right? And then let's say you had a data set of these blurry things, and you have the corresponding labeled unblurry thing here, right? So the brute force approach would be, okay, you get a data set of, let's say let's call this your blurries, the Y and X. So you get a data set of these YI and XI. And let's say a brute force would be, okay, I'm just going to train a CNN to go from here to here, right? So that could work, but you know that there is this type of relationship that's happening with this convolution, right? So actually you could, and what CNNs are going to be doing, they don't do, let's say, large scale convolutions, but they do current convolutions with these 3x3 things, right? So that may not be as expressive as the kernel that you have here. So in my case, for example, my blur is as big as the image. So the best way to do a convolution is not directly in the spatial domain, but do you know this in signal and systems? If you have a large convolution, where is it better, more efficient to do? In the Fourier domain, yeah. So we would take, let's say in a signal processing way, the way you would deblur this would be that you would take the FFT of X, and let's say you know somehow your kernel, let's call it P, and you would do some sort of Wiener filtering, or let's say you could do some inversion technique where you do Fourier transform of your kernel, and then that would somehow do some sort of deconvolution of this image so that you could get to, let's say, an X hat in the frequency domain, which is a deblurred version. So what you could do is you could add this convolution as like a preprocessor. Let's say you have a CNN. And here you have some sort of, let's call this inversion. What you could do is then you could feed your blurry things here, Y. And then as your inversion, you can have a parameter where you actually try to learn your best deblurring thing. So your P can even be a parameter here. So you learn the best way to deblur it. Sorry if you don't see it so well there. You learn the best way to deblur it. And then you're just using a CNN maybe to do some small, let's say, enhancements at the end of the outputs. And this way you can use a much smaller CNN here. And then you can, you know the operations that you need to do to generally deblur it, but then you can add some, let's say, perceptual enhancements to make it a bit better. So this is the technique that, yeah, they use in some, let's say, imaging tasks where yeah, they don't want to gather as much data, but then we can put in some bias because we know that there's this type of relationship we need to undo. Does that make sense? Okay.
Yeah, and then they usually put before the CNN. I mean, always put before the CNN, or you can also use it on the output side. Well,
you want to use it before because otherwise your CNN is going to might try to do this deconvolution thing. Whereas there's some equations to do the deconvolution. So first you do it, and then you can apply your CNN, and then you can treat parameters in your inversion as you can learn, like maybe you get an estimate of this, but it's probably going to be wrong. But then you can learn it through data in a way.
Or you backprop through the CNN and
you backprop through both, yeah, and the inversion thing. Yeah. So this is a technique I use a lot.
No, I was just wondering whether in other applications where you're trying to introduce physical domain knowledge,
yeah,
is it always at the beginning?
Usually it's at the beginning. You usually parameterize your, let's say, your model-based approach, and you do that at the beginning. And then what people do is they would add a post-processing thing to kind of clean up. But the nice thing is you don't need as big of a model as if you did this just brute force approach. So in audio, you could also do this. For example, let's say you can give an audio example. You want an audio example? So for example, if you think of like Amazon, like a Google Home device, or let's think of an Amazon Echo kind of thing. Maybe it has 4 microphones on the device. And there's techniques in audio signal processing, so multi-microphone processing known as beamforming. Who's heard about this? Okay. So the idea there is that it's, your normal filtering, so that you have this frequency and so low frequencies here, high frequencies there. Maybe you would filter so that you want to boost low frequencies or you want to boost high frequencies. So you're perhaps all familiar with those type of filters. But when you have multiple microphones, actually you can do something which is called beamforming, which is essentially some sort of spatial filtering. So essentially, if we look at a plot like this, which is a full 360 degrees, we can spatially filter maybe towards 90 degrees here with 4 microphones there. And the way we do that is by sort of adding their signals and delaying them in a way so that, let me give a 2 microphone example. So if a signal is coming from here, essentially, if you add these 2 signals, it's going to be increasing the signal in that direction. If there's a source coming from here, depending on the spacing here, you'd want to like subtract the signals to kind of focus in that direction. So essentially, you know that there's approaches to do that, which essentially increase the intelligibility of the signal. So what you could do, similar to the other approach, is that you have your multi-microphone signals here, and you'd pass it through like a beamformer block, and then you would pass it through maybe then you're trying to do something like ASR, which I guess you saw with Peter, right? Speech recognition. So maybe then there's some parameters for the beamformer, like the way you combine these signals, you can combine them in a nonlinear way that then you can use it jointly with an ASR to have better performance. So that's
what did you learn that? Beamforming is 1940s.
Yeah, it is. But it's all using just linear processing.
Yeah.
And maybe there's some nonlinear effects that we don't know necessarily the model, and the idea is to let the data kind of help steer the weights of these beamforming parameters. So that's kind of the idea. I mean, it's essentially, I mean, I like this expression, all models are wrong, but some are useful. So beamforming is a useful model, but it's wrong. I mean, it's a simplification, and we have to do simplifications when we do most of our processing. But then with machine learning, deep learning, you can then use data to help parameterize a model, which it should look like that, and hopefully get a boost in performance. So I can share a paper from this that I remember from Amazon back in the days when I was working audio, where they were doing this type of stuff, where they would learn the beamformer with an ASR and they saw a boost in performance. So, but all that to say, these are ways that you can add biases into your architecture. A lot of it becomes very application specific, but then that's where you really get like pretty significant gains and avoid also having to collect huge data sets. And so it becomes more practical. So that's what's interesting. If you can come with your own domain knowledge using some of the techniques that you start to learn with machine learning. All right, that was a long detour for this. Any other questions? No. Okay. So from that paper, an image is worth 16 by 16 words, which is an amazing title. Even they themselves, so they use these terminologies that we say. So in their paper, essentially, they pre-trained this vision transformer on large data sets, and then they showed its utility by fine-tuning it to many smaller downstream tasks. So that's another term you'll hear often, downstream. It's like your own use case, essentially. And so I have an example that we can go through together. So essentially, this model will take, so I can leave the presentation, make this bigger. So essentially, we're going to fine tune. So I put the link to the model card on Hugging Face. So this is the term that people use when they talk about models on Hugging Face. So this is the model card. So we can see you have, it's really similar to GitHub. A lot of people have their own username. So here Google has their own account where they've open sourced this model. And so we're going to fine tune, we're going to see how to fine tune this. In some models, what's really nice, you can actually test the model on Hugging Face itself. So for example, this is a very similar, I'm not sure what the difference is. I think maybe it's the number of classes they train it on, but this one, they have this inference API where here I can add an image. So I have this image of a whale, and then I can see, okay, what are the type of performance it could give? So this is a useful feature that Hugging Face provides, where if you're trying to pick a model, because there's like thousands and thousands of models you can pick from, maybe you can just throw in some images to see how it just performs without having to really run any code. So this is quite nice. And what's nice here, they also say what data set they used, and we'll come to what these spaces mean. And they give a lot of information, like in a GitHub README, how they trained it and whatnot, if they did a good job. And what's nice is if you want to use the model, there's just a little button here. And then, so Hugging Face has made this library called Transformers. Are you familiar with it? So essentially they built it with all this Transformers hype, but now there's so many things. But essentially they just give you like the couple lines of code that you need in order to load this pre-trained model. For example, you can load it this way. If you want to then fine tune, this is more like if you want to use it out of the box, I think, this pipeline approach. All right, so the slides you don't have. So I don't know if you guys want to follow along while we do this notebook. Should I show you the link to the slides so you have the links? So yeah, nice thing with Hugging Face, although it can be quite overwhelming sometimes. So that's why I've tried to use these slides to kind of concatenate all the nice fine-tuning examples. So they have this very easy to run fine-tuning example for this vision transformer using the Transformers library. So it's a blog post, which I've linked here. And what's nice with a lot of their blog posts is that you can then, they have this open collab button, which you can then press. And then now we can run this little example that they've created. So essentially, we see the same figure that we saw before. He's introducing what a vision transformer is. And as I said before, you take an image, you split it up into patches, embed each patch, and then tokenize and whatnot, do some deep learning magic with transformers. Essentially, they just took an architecture that worked really well with LLMs, and they realized, okay, why not essentially pre-process our vision, our images, so that it fits into this LLM training landscape. So I'm just going to try running all of them. And we can walk through it a bit. So yeah, essentially the main stuff is installing the necessary packages. Here they load the data set. So this is a really neat thing with Hugging Face, is that they also have this package. I can make this bigger. Hopefully that's better. Is that better? Okay. So they also have this datasets package, which is essentially a sort of API which links to a bunch of data sets which are stored on Hugging Face. So we'll come to that in a bit. So he prepared this beans dataset, which is essentially a dataset to detect healthy or unhealthy beans. So now it's downloading the dataset. So you'll see something like that. And then we can visualize the data sets. So here he just, when you print the data set like this, or also when you print models, what's nice is then you can kind of, it helps for debugging. So here we can see there's a training set with 1,000 examples, it tests a validation with about 100, and it tests that with about 100 examples. And then here we can see the different features. So usually when you're going to be coming with your own data sets to fine tune, what's going to take a lot of time is actually probably preparing the data sets in the format that Hugging Face's APIs are happy with. So essentially, you want to use this data set dict object, which itself has a few types of data sets, and you just have to do a lot of pattern matching to make sure your data set kind of fits in the structure that the model is expecting. So then you can index the data to kind of look at it. Okay, here you have to press yes. So here he's doing some other data set preparation stuff. Oh, I think I went too quickly there. Okay. Yeah, I jumped a bit there. Okay, so this feature, okay, I jumped quite a bit. Went all the way to the bottom. Let me go back up here. Okay. Okay, so here we can visualize one of the images, just like this. Can see its labels. Now here he's defining a sort of viewer to view multiple examples at the same time. So this is a lot of boilerplate code, which you can copy in your context. So here he plots different images with the corresponding label. So you can see, to get an idea of what's the data you're working with. And that's usually useful before actually training with your data to see, okay, if it makes sense, because otherwise if you launch a training and your data is completely corrupted, like for example, maybe all of these were black images and you didn't realize it until you started training. So it's good to just kind of visualize your data set before, or if there was some bad normalization and for some reason there's some clipping or whatnot. So that's good to do before. So here we see that essentially he's loading something called a feature extractor, which is similar to this preprocessor, which I mentioned before. So here he wants to load the same preprocessor that was used to train, oh, I jumped a bit, that was used to train this model that we're going to fine tune. So he just wants to make sure I load the same preprocessing kind of block to do that. So then you can also print the feature extractor to see, okay, what's different parameters it has set. Then you can apply it on an image to see what it would give. So here you can specify if you want it to return a PyTorch tensor or if you want NumPy tensor. So that will also depend on the model, what it expects. Okay, here's some more stuff to kind of allow that feature extractor to work on batches, because probably as you saw, it's more efficient to train on batches rather than one image at a time. So here he's essentially creating a function so that he can do this feature extraction first on the whole data sets, actually here. Okay, also from the data sets, he's going to load a metric that we're going to use to kind of follow how our performance is over multiple epochs or training steps. So here, just going to use accuracy. And he defines that metric internally here. And then this is the part where he actually loads the pre-trained model. So this would have been similar, like if we were at this step where we say use this model transformers. Essentially, okay, this is the pipeline approach. So it's a bit different. It's more like this one. It could have also changed. So here he's just, okay, there's different classes you can use. So you probably want to see the documentation why you'd use this one rather than this one. But I think this is one that was probably prepared by Google themselves, where you can say, okay, I've made a kind of API for vision transformers, which then you can specify the type of model you want. Here he's setting the number of labels, which I think are just, or maybe there's more labels. I think there's 37 or so. And then here just some other information that the model needs to know, okay, what are the labels that it needs to then output, and just to make the correspondence between what's in the data set. Okay, so there we've loaded if we look at our steps again here, we've identified our task. We want to detect healthy or unhealthy beans. We've identified a model. We've loaded that model. We've prepared our data set. Now we're going to go to that fourth step of defining a training configuration. So here, essentially, there's a few parameters, like you can set the batch size, how many epochs you want to train for, how often you want to see some updates. This part, he was saying it's important to keep false in this situation. Here, you can also already, through this configuration, decide if you want to already upload your new model to Hugging Face. So essentially, this is also in the transformers thing where they tried to provide some utilities for defining these training arguments. And then they have this like all-powerful trainer class, which then you pass your model and your training arguments and your metrics and your data set, and then it's just going to launch the training. So here it's configuring the training, and then essentially we just run trainer.train. And then here we see that it ran it for 4 epochs. And kind of here we just set, it's giving evaluations at every 100 steps, because that's what we specified in the trainer arguments. So it helps to avoid a lot of boilerplate code, especially if you just want to take an out of the box pre-trained model and fine tune it for your case. And the main work in this workflow is preparing your data sets so that you can pass it to this trainer object in a format that it likes. And then you can, within this part, define how long you want to train, what learning rate you want to use. So those would be parameters that you would start to play with. And it seems like a lot of little things to adjust, but it's much less work than having to train a vision transformer from scratch or a CNN from scratch. So this transformers library from Hugging Face is super powerful for do that. And you can use it for vision tasks, as we see here, but also we'll see it in a bit for LLM tasks. So yeah, that's essentially kind of a walkthrough of this notebook. Yeah.
Why does it stop after 40 bucks? Was that just to show, demonstrate? I didn't see.
So that's what that's what was said here. Yeah. So yeah, the documentation for Hugging Face can be quite intense. When you open, for example, this trainers class or the trainer config class. So I think here I show it. Let me open it here. There's a lot of parameters. Okay, this one's decent. There's only 11, but if you look at training config, there you have some crazy stuff. So it takes some patience to get used to it, but this is a lot of the work nowadays. And I guess machine learning is okay. Trying to understand which parameters work best, digging in Stack Overflow, okay, or looking at other examples like this one to know which are the most important ones to tweak. Any other examples on this notebook?
So here the 4 is an example just so you can run it in the.
Yeah, but usually a few epochs is fine, especially if you have a large enough data set. It could be good enough, but again, you'd want to see the evaluation metrics if it's getting to an accuracy 1. Here we get to like 97% accuracy. It was actually even better before. So it's already very high, the accuracy. I'm not sure what the initial one was, but yeah.
Just for clarification here, they are not introducing any biases, right? So there is no domain knowledge.
No, there's no domain knowledge. So here they're exploiting the fact that I have a large model that knows how to deal with images, and then I'm going to just fine tune it for my healthy, unhealthy beans situation.
For something like this, do you have data that, so the data you showed were 3 channels?
Yeah.
If you had more channels, fewer channels, can you still, maybe you have to do some extra work to exploit the base model?
So if you had, if you had single channel case, one trick would you just repeat that same channel across RGB. You're going to be doing more processing than you need to do. Yeah, that's one approach. If you have more like hyperspectral data, I think you'd have to put it back into RGB, but then you maybe would be losing information that you found interesting. Yeah, that would have been useful in the original data.
So then there starts to become a mismatch between the pre-training versus the task. Yeah,
because there it's, you kind of need, because there when you're working at those early layers, there you start to have to have to do things by scratch there, because now you need maybe a custom thing which can then work with hyperspectral data in that situation.
See, I mean, ultimately, you just care about edges,
Yeah.
structures of edges. So the features are going to be the same in the visual domain.
Yeah. So I mean, it could be then what you do is if you have, let's say, 9 hyperspectral channels, then you just fit 3 at a time into this if you want to get some sort of detection. Maybe you figure out a smart way of grouping which 3 should go together. But yeah. Any other questions on this vision task? All right. So I already mentioned it, but I'll point out to make it a bit clearer some of the conveniences of working with Hugging Face for doing this fine-tuning task. So essentially, they provide really nice utilities for storing and loading data sets, like we saw, storing and loading models, this trainer class for training and fine-tuning, and then one thing I didn't talk about yet is this Hugging Face spaces for demos. So they give a lot of things for like really start to finish for machine learning. So for loading data sets, so for example, in this situation, we were using this data set called Beans, which is hosted here. And what's nice is that you can visualize your data sets. So I've had to work with some data sets where people just put it on Google Drive or Dropbox as a zip. And that was such a pain because then essentially you had to download 80 gigabytes to even see if this data set looks interesting. And so what I've done in my own research and what you can see in this case is that you can actually see the images yourself through their interface, which is quite useful. And then similar in the model situation, if you want to download the data set, it's just a couple lines of code which you can copy from there. And then they have some smart caching and storing so that, yeah, you don't have to re-download the data set each time, of course, if you already downloaded it through this way. So this is quite nice. And then you can also see what models have been trained with this data set if people made that link, how many examples and whatnot. And then you have all these different tags, which you can then filter by data sets when you search for them. So I have to move this thing. So here there's this data sets where you can search for data sets or models. Okay, so there's that data sets part. Storing and loading models. So as we saw already, we can specify a path where essentially the Hugging Face username, the model, and then you can also push your own models, which you can then share with people, and then define your own ways of loading pre-trained models. So that's what we saw here. And then in some cases, like we saw, you can test the model through the interface. So that's quite nice. Or if you want to use it, they give you the few lines of code that you need. We saw also this trainer class where, okay, there's this 3-step process. You first define your training arguments, like we saw. You pass it to trainer along with your data set and the metrics you want to follow. And then essentially just these set of commands for launching and training, and then for launching and evaluation. And it's all handled by this trainer class, which is really, really useful. So one part we didn't talk about was Hugging Face spaces. So here you can essentially host your model and then have like a graphical interface for people to try it out. So for example, I don't know if I go to the space here or to this website here, let me try picking one of these and see if it runs. So here, let's see, I can enter a prompt, pizza party. I don't know what this thing is supposed to do, but I guess it'll generate probably a picture of this. And essentially you can host your vision model or your LM or generative models through this platform, and it makes the link to the model that you've pushed to GitHub. So yeah, here we see a picture of a pizza. So Hugging Face provides this nice feature for having these quick demos from some stuff that you fine-tuned. All right, any questions on those Hugging Face libraries? We'll see one more in a bit. Okay, so now we can switch to NLP LMs. This is not my forte. I don't do a lot of it, so I'll let Parser correct me if I say anything wrong. So probably some of you are familiar with this concept of prompt engineering. Have you heard about this? So just to lay out some differences, pros and cons between the two of them. So what's nice about prompt engineering is that you don't need any data to get started. You can already use the model that you're interested in from the get-go. And essentially the idea is that you try to put as much context into the prompt so that you can steer, let's say, this LM to respond in a way that you're interested in. So there's a smaller cost because of this, since you don't need to train. And then you can connect it with a technique called RAG. Have you guys seen RAG or heard about it? So you can connect it with RAG. And here I put a link to a tutorial that we had with someone from LumIndex to then augment it with your own local data. So you don't need to train with it, but then it can query from that data when you do requests to the LLM. So some cons though with prompting is that there's a limited, let's say, you could think of memory or context that you can fit into the prompt, or it may also incorrectly retrieve things from your external data sets. And then as we mentioned before, these generalized models weren't necessarily trained for a specific use case, so they could hallucinate even if you use RAG sometimes. And then it can be expensive if you have to do a lot of these at scale, a lot of these API calls, or if you're using a large model. So with regards to fine tuning, as we already saw for vision, you can use all of your available data to ideally improve the performance for your specific use case. It can be less cost than if you use a smaller model and if you run it locally. And it can also be combined with RAG as prompting. So there's this technique called RAFT, which is, I guess, retrieval augmentation with fine tuning or something. So I put a link here to that technique. But yeah, some of the drawbacks. So you typically need pretty good quality data to fine tune it. Otherwise, it will not perform super well. And then as we saw, we have to actually train it. So there's some costs that come with this. So in general, prompting is good if you want to do some quick projects, a prototype, or if you're at a hackathon where you don't have the time to train, you just want to see, okay, how can something work out of the box? Whereas if you really want to have something that's very specific to your use case and really ensure a better quality that you can actually test on through a data set, since you train or in testing with a data set ideally, you'd probably go for something like fine tuning. And yeah, there's this nice online short course on fine tuning LMs, which helped me with this pros and cons, which is also quite useful. So here I have another video. Now I lost audio this time. What did I do before?
You turn off your microphone.
I guess we can stop the recording here, so because we don't need to stream this video to them, they can watch it. What's actually happening in transformers? So this is a great blog where he shows what's happening inside a transformer. So he's applying LoRa to these Q matrices there. But it may seem kind of like, how does he know it's called QLin? Because there's one thing that he skipped, which may not be clear, is that when I think if you can see it from here. So in a similar way that he prints the data sets to see the data, you can also print the model to see the parameters. And when you print the model, you essentially see these QLin, KLin, and VLin. So actually, when you print the model, then you can see from there, okay, what do I want to set as the target modules to apply LoRa to? So for example, when I did his case with just QLin, so like here, actually it didn't improve performance for me. So I just added the other two matrices that are in this attention mechanism, and then it got much better. So then that's another hyperparameter you can play with if you were to use LoRa. But essentially, this LoRa is coming from a package that he mentioned called PEFT for parameter efficient fine tuning. So it's that third type of fine tuning he mentioned, where you keep everything frozen and you add these adaptive parts. And yeah, as you saw, that workflow that we saw for LMs was very similar to the vision transformer. And then this PEFT library you can also use in the vision context, not just LLM. So here I just put the link to that library. And what people also use instead of LoRa is also something called QLoRa, which is an improvement on LoRa in the sense that it can reduce the memory much further because it relies on quantization, and it also relies on some tricks between CPU and GPU sharing, which I'm not super familiar with, but the main thing is this quantization, which is why they add this Q part to it. So here's the link to that paper. You saw LoRa and QLoRa during the other sessions, or? Okay, so this is just an okay. So yeah, this is just an overview of it, but like here are the links if you want to dive deeper. But what's really nice in Hugging Face is they have all of these libraries for everything, and then essentially, as you saw in his code, you just have to wrap your model around. So this is the initial model, and he uses get PFT model with the configuration to then get this new model, which essentially uses this LoRa trick. So it's simple couple liners to get to that. And then he had this nice printing thing where you can see, okay, what is the percentage of parameters you're actually having to train now? So that's really neat. Any questions on that example that I gave? Okay.
Maybe.
Yeah.
Question. So I don't have like a clear question in my head, but
Oh, sorry. The
you-
pizza is calling. Maybe Parsa can try to answer.
yeah. Do we somehow exploit the fact that we use low rank approximation for this delta W, like except the fact that we want just have less parameters?
Oh, I see.
Do we?
You mean if we use full matrix?
No. We
It's
do
with that-
like No. I understand why we want to have like, less parameters. We want to,
Yeah, from the efficiency, of course.
but why? Like there are maybe many different ways how you can like reduce the number of parameters in the matrix. Why we use low rank approximation?
I think the motivation was that the general idea of matrix factorization can be stuff. You have two matrices that one of them will be a lower number of for the first one the number of rows, for the second the number of columns, like that. So when you have it do like this, you can show the whole matrix with a lot less points.
Yeah.
And so this is the motivation. But I think your question is you are saying if there is any benefit other than efficiency.
Is there any intuition why we want to have their low rank matrix?
You mean why not any other method of comparison matrix? Yeah, but what is the other method that you like? This is one of the methods that people compare matrices. I mean, the other one, like the way to make matrices sparse. Oh, that's good.
No, you can just.
Yeah, I mean, the one that
like,
comes to my mind,
by
of course, always usually showing matrices as a multiplication of a smaller matrix, which is the same thing. But yeah, but I didn't say it's a bit like it's easily formed in this format. You can, but yeah, you can. I think the people have actually this kind of like three matrices, like one diagonal, like this and that.
Oh, I see. Yeah, but for example.
It's a good question. I don't think people have tried it.
Also, so you can think like with this interpretation of two matrices, so you can think of like learning some basis vectors and then just like taking their like linear combinations.
Yeah.
And again, so you can take any basis vectors in basis or like random vectors and
I see.
learn weights.
Try it or
I think this should be similar to some
both
organization.
Yeah.
no rank approximation is the way to increase efficiency. What other ways to also represent a big matrix into a smaller form? For example, a PCA kind of thing, or like split into three matrices. I think they have been used in NLP.
I am not an NLP enough to know, but I think what's good about the low rank is that it's just a matrix vector. I mean, just matrix multiplication, and that's what GPUs are really good at. Because if you have to do PCA, doing an SVD is quite an expensive operation. I mean, they could do, but it's more expensive than doing so you want to do an SVD decomposition on the original thing and then do a low rank approximation of the original? Is that the idea, or?
So I think that a clear question. I think, but yeah, so there are like many ways when you can have low rank approximation of your matrix. Or what you can do also maybe this might help to reduce overfitting, so you can have like a specific number of basis vectors and then just train with the second matrix with weights. I don't know. For example, you can take Gaussian vectors. Then your first matrix. I don't know.
Yeah, I mean, I guess there's multiple. I guess when people when they discover LoRa, I'm sure they tried many different things for low rank approximation. And and they just include this, and then a lot of machine learning researchers like that. They try many things, and then they try to explain it. And then they say, okay, it makes sense for this, and then they do different experiments to show how it holds to make sure, okay, this is actually a finding. So it's a very experimental field. but I'm sure there's other ways, because you could probably do this piece or this SVD on the original matrices to do a low rank on the original things, because here he's adding an extra thing. And maybe that's one way if you combine that with quantization to make a model even smaller. Yeah, it would probably need more training than just this technique, because in this technique, there's still the original model, and then they're just adding some extra parameters which maybe help steer it to their use case. Because I don't have a clear idea as to why adding this delta W is better, but I think it's just there's a computational reason why it's better, at least.
They don't touch the original ones.
Yeah.
It's kind of freezing as well.
It's kind of what?
Kind of freezing as well.
Yeah, I mean, it's because it could be that this delta W ends up being 0, that it could be that the original was fine enough. And in some cases it'll be 0, other cases it won't. And then, yeah, it's a nice hack to exploit the original one, but then adapt it as you need. In the
head on top, like in parallel. As they
Yeah.
in their paper.
Yeah.
With like the matrix, and then there's the A and B, if the original figure like this, they do it in parallel.
Yeah.
So do you know, is there any restriction on the size of the delta W?
It has to be the same final shape as the original matrices. It's just, well, you can change the rank. So how?
I understand that, but I meant the magnitude of the weights. So because if you'll find
See.
feeling is that it should be small adjustments.
I guess that's why he calls it W, but maybe you could add some regularizations so that they don't explode too. I don't know. I haven't trained LoRa myself to know, except for these small examples.
Be well and not to be learned, because the base models are good
Yeah.
overall, and they just to me find it for that. So the gradients would never be so big, so that the
So it wouldn't be dominant, basically.
I don't think so.
Like the base
Because
model.
if the type of general similar, there won't be any big gradient.
Yeah, I would have to, maybe in their paper they did some visualizations of the weights. I don't know off the top of my head. So how's the time? We'll try and close up now. So yeah, the next slides are just, they're not even slides, they're just slides with links. So if you want to dig deeper into audio tasks, I put some links to classification of audio events, to ASR if you want to do like full speech transcription, and also the text to speech aspects. So here's some examples of fine tuning for those situations. For image generation, yeah, Hugging Face also has a nice tutorial on diffusion models if you want to fine tune it to generate a particular type of image. So in this one, they took, I think, a model that was originally trained for celeb faces, and then they tried to fine tune it for generating butterflies. The results are still catastrophic because I think you need a lot more training, but it gives you an idea of what is the procedure. And it's really the same stuff as we were seeing before. You identify the base model, prepare your data sets, define your training scheme or technique to fine tune, train, evaluate. And I'll say some quick things on zero-shot classification, which I think you already saw a bit before. So you guys saw this clip model already? Yes? Okay. So essentially, this is something that has been trained to produce both a text encoder and an image encoder, which can work in a similar space to compare them. And in the space that they compare, they use this cosine similarity to then see if an image is close to a text. So for example, here's a visualization of it, which you may have seen from OpenAI, where they can compute a confusion matrix between image and text pairs, and then you can see which ones are more likely to correspond to each other. Like if you're describing the puppy, I guess that score, this score would be higher for that particular pair. So I've also put a link here on how you could do zero shots. So here as before, they load this clip model from a pre-trained. They also load its preprocessor. Here they want to test this cat picture. And what they do for zero-shot learning, if you want to, let's say, detect if something is a cat or a dog, you can pass it to this processor with all their classes. So here, a photo of a cat, photo of a dog, but you could add a photo of a zebra, a photo of a blah, 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 blah. And then you pass your images, and then it's going to compute essentially all the image, text, pairwise things. And then when you see the scores, you'll see that, okay, the score for a photo of a cat with the image is much larger than for the dog example. So that's how you could do zero-shot learning. And the reason it's zero-shot is because there's no training involved here. We're using these pre-trained encoders to kind of match these inputs from different modalities. Any questions on that? Locally, could I run it on my laptop? I probably on my Mac for sure. I guess on CPU you could run it as well, but yeah, there's no training involved here. So, and you could do the same thing with audio. And I found this name to be genius. It's called CLAP. So it's contrastive language audio pre-training. And essentially they've trained a similar model with audio and text pairs. So then you can do the same thing where here they loaded an audio of a dog, and then they have these candidates labels or classes, which is a sound of a dog, sound of a vacuum cleaner, but you could add a sound of a truck, a sound of blah, blah, blah. And then again, you'd get these similar audio text pairs. So here there's an example of the dog score is much larger than the vacuum cleaner. And so this example is from, I'm just going to point to another really great resource. This is Deep Learning AI, which is a bunch of short courses where they have like these paired videos and side-by-side notebooks. And so essentially then you can run this whole thing to then hear it, because in this case it's not visual, so you can't hear it. So let's see if it'll run in this meantime. And so this is a short course that this website has on how to use open source models from Hugging Face. So it's essentially what we were seeing here before. So for example, in this case, here's right here. Huh? It's a very tiny dog barking, maybe. But I guess at least between, that's how they labeled it.
I want to know what the model thinks.
But I mean, it's the screenshot I showed before where you do the 0-shot classifier where you pass the audio example you want to test, and then the candidate labels, which are sound of a dog and vacuum cleaner. And then, yeah, it has this 98%, 99, almost 100% for dog versus 0 for vacuum cleaner. So I could do this similar 0-shot for audio as you see with text and images. And then if you have any of these encoding pairs, then you can do these 0-shot learning, but you need a base model.
More interesting.
Which one? Huh?
So 18.
Yeah, so this one, it's in none of those classes, actually. And then you can see that the scores are much lower. So it thinks the closest is a bird singing out of these, but it's not as high as the dog. So it's 61% in this case. So yeah, that's on 0 shots. So in summary, models are getting bigger and bigger, especially with transformers kind of being a go-to architecture in a lot of different spaces. And since they're difficult to train and require a lot of data, the common approach is you take this pre-trained model, and then we're going to fine-tune it for our particular task and the data that we've collected or that we found. And then a really useful pro tip to kind of speed up your workflows to use these Hugging Face tools to help you load these models and data sets, and then also to do stuff like these performance efficient training techniques like LoRa. And then this is the steps that you'll see for any of these different modalities. And I guess if I were to add another step is essentially find a tutorial that does something similar to you're doing. So that's why I tried to put different modalities here for you, so you can come back and say, okay, if I want to do images or NLP or audio or image generation, they're there. But also Google search with Hugging, like fine-tuning both XXX with Hugging Face, you'll probably find a bunch of tutorials. That's a good way to go. So I'll just point out some of the Hugging Face courses, which were quite useful for helping me prepare. So they have all these different intro courses into all these different modalities. And then I mentioned this Deep Learning AI site where they also have a lot of these short courses. And I was using some stuff from this open source one. And then final notice about LauzHack. So if you haven't already, you can sign up for, not sign up, but pre-sign up for the hackathon, which will take place end of November. And then we'll let you know when the official sign up is out. And then we'll also be doing tech talks again, September. So those are like short 1 hour, 1 hour and a half, where we have someone maybe from industry or someone from EPFL present a topic, and then it always ends up with pizza like that. So that we'll be doing starting in September again. Yeah, that's it that I have for today. Thanks for your attention. And also thanks to Peter and Parsa for all the work that they did in preparing these last few weeks. It was a lot of stuff, and they did a lot of great coordination and also preparing material. So, round of applause for them. Any questions, or we can have questions over pizza? Pizza? Okay, cool.